Morning, everyone. So today we're going to be looking at stoichiometry. This is basically putting all the calculations we've seen up to this point here together. We're going to see molar mass conversions, molar volume conversions, maybe concentration come back again. But what we're going to be combining it with this time is also the balance equation. The balance equation actually serves as a recipe for us. It gives us some power in calculating. If I know the amounts of ingredients going into the reaction, I can calculate how much I would expect coming off of it. Just before we start into that I just want to do one quick practice question from our gas law section. So if you want to do this as a quick warm-up here, I want us here see if we can calculate the volume of 1 mole of gas. I'm not going to specify which one because we know that the volume actually doesn't care the identity of the gas. It just depends more so on the temperature and pressure. This time I'm going to specify here 1 mole of gas at 0 degrees Celsius and 1 bar pressure. I'm going to specify here as well using the ideal gas equation. Remember when we did this gas law section, we had two potential formulas. One was the combined gas law, which you have to memorize. P1V1 over T1 is equal to P2V2 over T2. We'll know to use that formula whenever there's a comparison between, okay, here's the before, here's the after, I'm changing the pressure, I'm changing the temperature, what is the new volume, that sort of question. In this case here, if I can just put down my letters, I know that 1 mole is going to be N. We know that we have 0 degrees here. I do need to convert this to absolute scale because it has to be in kelvins before it works in our formula. And I know I have pressure, but in this case here, there's no indication of changing conditions. We just want to know, well, what's the volume right now if I had this temperature and this pressure? So instead of using the combined gas law, we can look on our data table. We can use the ideal gas law, which they're mentioning here. PV is equal to nRT. You can even rearrange that a little bit here. I just wanted to compare based on these two comparisons. This one here, because I have sort of condition 1, condition 2, we just needed to make sure that these top units here were consistent. It really didn't have to be necessarily SI units. Whereas, and if I use ideal gas law, because I don't have that ratio set up, these ones here should really be in the SI units. That really is going to be the hard part in these ideal gas law questions. The formula itself is not all that bad. Let's just have a look together here. So pressure P, the SI unit here is supposed to be meter cube. Let's see if we can convert this 1 bar here. There will be some conversions you need to memorize here. 1 bar we know to be 100 kilopascals. Kilo is 1,000, so therefore it says 1 bar is actually 100,000 pascals. I know a big number there. We're going to get volume out in the SI unit. Volume's unit is supposed to be in meter cube, so I don't need that right now because I'm calculating for volume. Temperature I do need to change. So temperature here is currently 0 degrees Celsius. The SI unit for temperature for these formulas, it has to be in the Kelvin temperature. So I'm just going to rescale it here by 273, and that gives me here 273 Kelvin. You should actually already know the answer to this, but let's just punch our way through the formula. If I have PV is equal to nRT, you can of course punch the numbers in and then isolate afterwards, or I'm just going to rearrange the variables. In this question, I'm interested in finding volume. Volume is going to be the nRT divided by the P. Let's just punch our way through here. We have N being 1 mole. R here is actually 8.31 joule per Kelvin mole. That's the universal gas constant. That number is always going to stay the same for every problem that you do. The temperature I'm going to punch in is 273 Kelvin, and then I'm going to divide it by the 100,000 pascals in SI units. So let's just type that all in there. See what we get. 8.31 times 273 divided by our 100,000, and I'm getting here 0.0227. Again, because I used the SI units going into it, I'm going to get the SI unit for volume coming out of it. So this one here is going to be 0.227 meter cube. Does that number look familiar at all? Hopefully it does here. So meter cube, we know meter cube is equivalent to a kiloliter. If I expressed it back in decimeter cube, I would multiply by 1,000. This number is equivalent to 22.7 decimeter cube. So where have I seen this before? 1 mole of any gas is actually 22.7. You'll probably recognize that there, well, that's just a molar volume. That would mean for molar volume, that was at STP. Oh, right, this is standard temperature and this is standard pressure. So therefore, we've actually figured out where did they get that 22.7. Earlier, the standard pressure used to be a little bit higher. It used to be 1 atmosphere. 1 atmosphere here in the bottom number here, it used to be 101,325 Pascal. It would change this division by a little bit here. They got out 0.0224, and that's why in a lot of old textbooks here, you're going to see the conversion as listed for atmosphere. It's going to be 22.4 instead. We're just going to be using 22.7. Even the regular grade 11, grade 12 curriculum is slowly changing to using 22.7. So standard temperature and pressure are sort of nice because they sort of worked out and did all this math for you behind the scenes so that not every time you need to do this, if you recognize, oh, this is just our reference temperature, reference pressure, I can just go directly. 1 mole is 22.7. So hopefully that recaps a little bit of the gas laws stuff for you here. As I mentioned already, today we're going to be going into stoichiometry. We're going to be putting conversions like this in helping us compare recipe quantities. So this is sort of the ending of chapter 1 here. We're going to call this stoichiometry. Just let me give you a definition here. Stoichiometry is the study of quantitative relationships in a balanced equation. Right? So we're studying sort of the numerical relationships. We're using actually those coefficients as our proportions in the recipe to see if we can make predictions. Just like a recipe is no good to you unless you have all the proportions set up correctly, we want to double check that all our equations are properly written before we try to do this. We'll just do a quick analogy here. I like doing a s'mores analogy. So let's say we go out camping one day. We decide to make up some s'mores. So I'm going to come up with a recipe. There's many different recipes, but my recipe here, keep things simple. To make a s'more here, I'm going to take 2 graham crackers. So I'm just going to say 2 crackers here. We need marshmallows, so I'm going to melt maybe 3 marshmallows. Just going to write 3 marsh here. What else do I need for s'mores? Well, I need some chocolate, so let's melt in, just drawing my chocolates here as triangles here. 4 choco. I melt that all together and we get 1 delicious s'more. So that sort of serves as our recipe. Right? So again, we're just doing this as an analogy here. So even though that's my recipe, that's sort of my simplified ratio going into it, my store will probably not sell crackers just in units of 2 or marshmallows in 3. So let's say for argument's sake here, at first, when I buy a pack of crackers, my store actually packages them as 50 crackers. Right? I don't know, some sort of store does that. Could I ask you the question, if I have 50 crackers, right, can I still use the recipe? I wouldn't look at this recipe and be like, oh no, the recipe says 2. Well, no, the recipe says for every 2 that you use, you would need 3 parts marshmallows, 4 parts chocolate, and so on and so forth. The recipe just represents a ratio, it represents a proportion for us. So if I ask you this question here, if I have 50 crackers, how many s'mores could I potentially get if I use them all up? We can just simply do the ratio. Well, for every 2 crackers, for every 1 s'more, I'm only going to get half the number of s'mores. I know the answer should be 25. Just humor me for a second here. We're going to set this up with a unit conversion. So question mark s'mores here. We're starting off with 50 crackers. Always start off with the number that's given to you. The ingredient that I don't want here is crackers. I'm going to put crackers down here. What I want is I want to get s'mores. We've actually never seen this conversion before, but it turns out it's not that hard. Just like I would have coefficients in a balanced equation, I just take the numbers directly from the balanced equation. When there's a 2 in front of crackers, there should be a 1 in front of s'mores. That's where we pick up the divide by 2, and that's where we actually pick up 25 s'mores. What assumption have we made in doing that calculation? If I just went to buy 50 crackers, could I make any s'mores? Well, no. You actually need to assume that you have enough of the other ingredients. So many times when you're doing problems like this, if I'm asking, I have such and such this reactant, I'm looking for how many products, we are inherently making the assumption, assuming the marshmallows and chocolates in this case, assuming other reactants, assuming the other ingredients, here's the terminology, are in excess. Excess means, oh, maybe I had some leftover from another recipe or so. I didn't need to go rebuy marshmallows or rebuy chocolates. I'm not even going to get a good count on them because I actually know I have a ton of them left. So whenever we're interested just calculating from one thing to another thing, you can just pretend I have enough. I definitely have enough marshmallows, definitely have enough chocolates. We're going to do a problem in the next lesson. Well, what if I actually go to the store, I don't have a lot of leftover from another recipe. What if I have this many crackers and I buy this many marshmallows? Well, what would the in case one chemical run out first, how would the calculations change then? Let's do one more practice here and we'll switch over back to the chemistry analogy. So let's say in another setup, I happen to buy 90 marshmallows. Right, so maybe they come bagged up to us 90 marshmallows. I realize, oh, I've run out of chocolates. How many chocolates should I buy? What I want to show you with this analogy here is not only can we make comparisons between reactants and products, because the reactant and reactants are also in the same recipe, we can also jump reactant to reactant. So I could say, well, given my marshmallows are coming to us in a bag of 90, how many chocolates would I need? So again, this is a new example. Again, you can probably do it in your head here. Well, it's a 3 to 4 ratio. I'm expecting it to be 120, but let's have a look here. I'm looking for how many chocolates would I need. Here's 90 marshmallows. I don't want marshmallows anymore. I want to know the chocolates instead. Again, where I get the conversion factor is in my coefficients. When there's a 3 in front of marshmallows, there should be a 4 in front of chocolate. Marshmallow is down here, 3, 4 for chocolates here. You do that 4/3 ratio, and therefore we get 120 chocolates. So we're starting to see how the balance equation actually becomes a nice way to actually compare one ingredient to the other ingredient. So carry that s'mores analogy with you, and then we're going to do the chemistry context. We're going to start off here with just a plain old one-step conversion. Of course, they don't need to tell you how many conversions it's going to take, but as we're learning it, we're going to start from one step, and by the end of this lesson, we're going to do a 3-step conversion. So just like our s'mores analogy, we need a recipe. We need to know what are our ingredients and what are we trying to produce. In this case here, I'm going to give you, we have ammonia and we have oxygen, right? We have done a lot of like predicting simple reactions, classifying them or so. This one is a little bit harder, so I'm going to hint at what the products are. We're going to get water and we're going to get NO. First thing you're going to do is you're going to want to check whether this is balanced or not. Sometimes they even use the terminology here. This one here is either an unbalanced equation or it's what's called the skeletal equation. It's like the skeleton of an equation. What they're trying to tell you here is this is not yet balanced. So try it out for yourself. Again, there's no hard and fast rule for figuring out how to do this balancing, but you do want to, just by inspection, see if you can figure out what the numbers are going to be. Hopefully you're able to find here, it should be 4, 5, 6, 4. We want to have the simplest whole number ratio. That represents the proportions. Draw a picture of this here. So just like my s'mores analogy, I need 4 of these ammonias. I need 5 of these oxygens. I get 6 waters out of it, and I get 4 NOs. The question here is, when does this recipe work and when does this recipe when it doesn't work? As a general rule, we saw a little bit earlier on with Avogadro's law, it works whenever we're comparing numbers. So for example, if I go to the store and I actually have 4 molecules of NH3, well, of course, I'll need 5 molecules, 6 molecules of water form, 4 molecules of NO in a form. Again, this is just a proportion. So if I go to the store, I can also say, what if I have 40 molecules? I don't look at my recipe book and be like, oh, shoot, I need to find another recipe book that says 40. Well, I just scale it up, right? So for every 4, because I'm 10 times as much, that's going to now require 50 molecules. I produce 60 molecules of water, and I get 40 molecules of NO. Easy. What if this instead were 4 moles? Now, moles is going to be a whole lot more than just individual molecules. But again, mole in some sense is also a counting number. If I have 4 boxes full, if the ratio was 4 to 5, for every 4 particles, I need 5 parts oxygen. For every 4 boxes ammonia, this is actually going to be 5 boxes oxygen. And I'm going to get 6 boxes water, and I get 4 boxes nitrogen monoxide. So in general, whenever we compare numbers, this recipe was going to work. When does it not work? It actually usually doesn't work. So for example, what if I weighed out 4 grams of NH3? Could I come along and then say, well, here's the grams, 5 grams of oxygen, 6 grams of water, and, well, no, you'd say we did molar mass. If you do your periodic table here, this one weighs about 17. This one actually weighs 32. Mass actually means something totally different. So just to show you, the coefficients, they're nice in comparing number to number as a ratio, but it doesn't work for any other units like grams, like volume. It typically doesn't work. So we're going to figure out a strategy to make it work later on, but for the time being, we're just doing a number-to-number relationship. This is going to be, I'm going to focus on this line here. We're going to be using the coefficients in the balance equation to form what's referred to as a mole bridge or a mole ratio. Since this ratio here works comparing moles of one thing to moles of another, let's see if I can use this in my conversion. So we'll have a look together here. So I want to know here how many water moles can be produced from 2 moles of NH3. Right? Doesn't seem like that hard a question. You might, again, be able to do it in your head. If I have 2 moles of NH3, you just need to find it. NH3 is on the left-hand side here. If I have 2 of these, again, I wouldn't say, oh, this recipe says 4. I need to look up another recipe. The recipe just gives me the simplest proportions, the simplest ratio. It says for every 4, you get 6 parts. It's like a 3/2 sort of ratio. I could actually go, well, if I have 2 moles, I would expect I need to produce 3 moles of water. Again, humor me for a second here. We're going to set it up as a unit conversion. We're going to go question mark moles. As we start getting into the stoichiometry, we definitely are going to be comparing multiple chemicals with one another. So you might be good actually writing out the actual chemical beside the unit itself. So question mark moles of water if I start off with 2 moles of NH3. Let's tack on our unit conversion here, just like I did the, I don't want crackers anymore. I'm going to cancel out the moles of NH3. I want to get up to moles of water. Believe it or not, you actually haven't seen this conversion before. We've done grams to moles, moles to liters, moles to number, moles to atoms, things like that, but we haven't ever done moles to moles. This time, this is a new conversion, not a very hard one, but this time, this guy here is called your mole ratio, and what we're going to say is the numbers come from your balance equation. Again, important for you to note, make sure you have it balanced. So what this says here is when there's a 4 in front of NH3, there's a 6 in front of water. I know mathematically that ends up as a 3:2 ratio. I'd rather just leave it as 6 and 4. In case I make a mistake later on, I'll know where I got that 4, and I'll know where I got that 6 from. It's just as easy to type in your calculator here, 2 times 6 divided by 4, just like 2 times 3/2. And just like we said, it's going to be 3 moles. Just a comment on sig figs here. Do we have any problems? Most of our conversions here have been multiply and divide. Multiply and divide says you want to round it to the least significant figures. In this case here, the 2 moles is going to be a 2 sig fig number. How precise are these numbers here? Well, again, I can backtrack and I can figure out, well, where did I get that 4? Where did I get a 6 from? Those are directly from the recipe. The recipe says an exact 4 units of NH3 is 6 units of water. Because that is a small counting number, this one here is exact. This one here has infinite significant figures. Your final answer would just be limited by the precision on your starting measurement, the 2 moles of NH3. So we started seeing this conversion here is what I'm referring to as the mole ratio. So it's moles of one thing to moles of another because my balance equation gives us a nice comparison. All right, so that's a one-step conversion here. Let's make it one step harder. I mentioned previously here the ratio doesn't work when we're dealing with grams. So what if we actually have grams, or what if we're interested in finding grams? How can I utilize this ratio here to my advantage? So what I'm going to do, this part here is a 2-step. Again, just for our learning sake here, I'm just going to slowly increase the difficulty. We're just going to keep using this recipe. This recipe here could be any one in the question, but I just want to have some familiarity so we're used to looking at this. So we have 4NO here. So there's our balance equation here. Remember, in terms of balancing, after you balance, the multiple choice will typically say, what are the sum of the coefficients? So if I want you to add up all the coefficients, I add up 4 plus 5 plus 6 plus 4. I think that's 19. Or I might say, what are the sum on the reactant side? You can just add up the 4 and 5. You just look for the choice that adds it up. Make sure you add in the ones. So let's try a quick problem or two here. This time what I want, as an example, I want you to find for me how many grams of oxygen are needed to react, let's just totally make up a number here, 6 moles of ammonia. All right, so that's how the question is worded here. Usually in the word problem, they're going to add a little bit. Like earlier I had said, how much can be produced? In this case here, how much is reacted? They're just hinting at, based on the recipe, well, earlier, water happens to be a product. Of course, it gets created. So I use the term produced. In this case here, if I just sort of lay out my numbers here, I can say, well, I'm starting with 6 moles of ammonia. Remember, ammonia is a common name that you want to memorize here. Ammonia is NH3. I'm starting out with 6 moles. Notice I'm not changing the actual recipe. The recipe still says 4 to 5. This time what I'm comparing is, just like our marshmallow chocolate analogy, I'm going to actually compare. If I have this much of the one ingredient, how much of the other ingredient would I need? And let alone what they want is they actually want grams of oxygen. Where we said, wait a second, mass is actually different. How can we actually do this? So What we're going to actually do here is we're going to set it up the same way. I want to go question mark grams, oxygen here. I could say oxygen gas. Gas doesn't change the fact that it's oxygen, but it does need to be O2. So especially when I'm using molar mass, it has to be 2 times oxygen's mass. Start off with the number given. I'm currently only given the one number, 6 moles of ammonia. What I really want to say here is I want to go moles of one thing to grams of the other. But like we said already, this doesn't work. First thing I'm going to do is I'm going to get us closer. So far, I only have information about ammonia. I want to switch over and I want to tell you some information about oxygen. What we're going to start seeing is the only comparison between how much of one ingredient and how much of the other is through a mole ratio. So if I have moles of one thing, I can do a mole ratio and I can get moles of oxygen. And then you can probably extend that and you say, oh, if I know this many moles of oxygen, I know I can do molar mass of oxygen and we're all good. So that's why this ends up as a 2-step conversion. What I'm going to do at first, I'm going to do my new mole ratio. My mole ratio is moles of ammonia. I want to get to moles of oxygen. And then once I'm oxygen, I'm home free. I can just say, well, I know for oxygen, every oxygen weighs 16. There's 2 of them. It's actually going to be 32 grams per mole. Once I've jumped chemical, I'm back to using our regular old Avogadro number, molar mass, molar volume conversions again. So let's just try it out here. The new conversion. In the balance equation, when there's a 4 in front of NH3, there should be a 5 in front of oxygen. 4 in front of NH3, 5 in front of oxygen here. Once we're at oxygen, I don't really care anymore. I just say, well, 1 mole, the molar mass of oxygen is going to be 32.00. Numbers on top you multiply, on the bottom you divide. So I'm going to go 6 times 5 times 32 divided by 4. Again, keep track of your sig figs here. I'm getting here, it would actually need 240 grams of oxygen. So you see I've sort of worked around my problem here. I know my coefficient ratios, they don't work for masses. I couldn't jump straight from 6 moles straight to grams. But what I did is I used the ratio where it works, moles to moles. Once I've jumped chemical, I'm more than happy using molar mass and molar volume, those conversions again. One other note I want to show you here is sometimes people get confused. They say, oh yeah, oxygen here is diatomic, it's going to be 32. But what about 5 oxygen? Shouldn't I like 32 times 5? Because I actually have 5 parts there. What I want you to be careful, the 5 is important, but I want you to make sure you don't double count this 5. If I accidentally take the 32 and I actually multiply that by 5 and forget I've already multiplied the 5 here, I would have double counted that 5 there. So just for simplicity here, what we're going to do is we're going to make sure all our other conversions stay exactly the same. The numbers and the coefficients only enter the mole ratio step. Okay, so coefficients only enter the mole ratio conversion. And that way, if you know where you've accounted for them there, when you do molar mass, it's just for 1 mole. When you do Avogadro number, it's 6.02. You don't need to scale up that number. When you do 22.7, it's just for 1 mole. Even concentration, it's just for 1 mole. So that way, we don't accidentally double count. So let's just practice another 2-step one, and then we'll move on to a 3-step conversion. I want to figure out here how many decimeter cube of, so that's liters, nitrogen monoxide gas at SDP can be formed along with, let's say, 10 moles of water. And really, I'm not worried about, did they say, is reactor width has formed or whatever. Again, they're just hinting at, are we on the left side or on the right side? In this case, see if I can lay out my roadmap here. In this case, my final answer would be decimeter cubes of NO. NO here happens to be on the right-hand side here. I want to know question mark decimeter cube. I want to know how many liters. How much is formed along with, so this also gets produced, 10 moles of water. I'm given here 10 moles of the H2O instead. Again, usually the mole ratio works, moles to moles. Number ratio works, molecules to molecules. But again, it doesn't work moles straight to liters or moles straight to decimeter cube. So I'm going to sort of work around that. I'm going to say, well, my mole ratio does work going moles to moles. So let's do the 6:4 ratio. That's where it enters. And then if I have 1 mole of gas at SDP, we just did the conversion. 1 mole is always 22.7. Let's see how this ends up working out here. We're interested in how many decimeter cube. Remember, decimeter cube here is a liter. Start off with the number given, which is 10 moles of water. Based on my sort of roadmap here, I'm predicting it's going to take 2 steps. First one will jump chemicals. It'll jump from moles of water over to moles of NO. I'm going to then say here, for every however much moles of water, moles of NO. That's going to take care of my problem of jumping chemical. And now that I'm talking about NO, this is now going to be moles of NO to how many decimeter cube of NO. Because I know NO is a gas at STP, I can then use the ideal gas law, that molar volume that I got from earlier. When there's a 1 of NO under standard conditions, 22.7. The new conversion here was a balancing here. When there's a 6 in front of water, there's a 4 in front of NO. Sometimes your recipe may even have the same coefficients. Let's say this had instead been comparing NH3 to NO. Both of them happen to be 4. I would still show the ratio times 4 divided by 4, but I wouldn't bother typing it in because I would end up just multiplying by 1. So that way you can trace your steps a little bit here. Numbers on top you multiply. 10 times 4 times 22.7. I'm going to divide out the 6, and I get to your safe fix here, 151 decimeter cube. No problem if you put your answer in 151 liters, but just note that when they give you questions, they're definitely going to use the frame of decimeter cube instead of using liters. Let's move on now to our sort of last complexity for today. Let's move on here to a 3-step conversion. Let's think about how I might set up the question so that you actually need to do 3 conversions instead of the 1 or the 2 we've done so far. Again, just for familiarity's sake here, I'm just going to keep using the same equation. On your worksheet, you're going to have a bunch more different recipes. You might need to balance it. The coefficients will be all different, but just for simplicity, let's just work this way. So let's say I'm interested in, see if you can find for me how many oxygen molecules are needed to produce, okay, so that hints at products, to produce, let's make it here 25 grams of water. Right. So usually what I try to do here is I try to convert what would be a word problem. I try to put in the number, see if I can hint at, well, what's my heading? What's my direction? How can I actually get to it? So for starters, my very fine answer is going to be molecules of oxygen. I look for oxygen in my recipe here. Oxygen is a reactant. I'm looking for question mark molecules of this thing. That's what I want to know. Great, molecules is even a number. I'm kind of on the right track. However, unfortunately, what they give you is they give you mass, so they give you grams. I know my mole ratio doesn't work for grams. And they also give it to you for another chemical. They actually give it to you for water. They say produce because water happens to be on the product side. So this is definitely not a nice conversion. Because I know my mole ratio works moles of one thing to moles of another. I'm actually going to employ that, but it doesn't work when we start factoring the molar mass of this one. Now we actually want molecules. Now we need Avogadro's number. That's fine. We're going to use the same generalization. The mole ratio works whenever it's moles of one thing to moles of another. Could you get moles if I gave you grams of water? Well, sure. Do the molar mass of water. Once you have moles, I can do the mole ratio, moles to moles. Once I've jumped over to oxygen, I've done the hard part of the question, then I can say, oh, I know, 1 box is Avogadro's number. And therefore, I've actually converted it in our 3-step conversion. After we do this problem here, I'm going to show you that summary diagram again. I'm showing you what we did. It's nice if you can do this all in one long row. So how many molecules of oxygen? We're going to start off with the one and only number that I got. Let's work through our conversions here. Let me just emphasize, this is 25 grams of water. First conversion gets rid of grams and goes just to moles of water. Right? I haven't jumped chemical yet. It's only in the next step that I actually jump chemical. Jump over from here's how much water gets produced, how much oxygen are you putting in, moles of water to moles of oxygen. That's why it starts becoming important. By putting that chemical down, I know which chemicals I'm jumping to and from. And in this case, once I've taken care of the problem, I've jumped from the information I know about water to over to oxygen. I can say, wait, if I have this many moles of oxygen, how many molecules? I crack open the box and I count how many are inside. Let's go through and put a 1 beside the bigger thing here. I know 1 box is bigger. I know 1 box is for oxygen is bigger as well. The numbers for the mole ratio come from the coefficients. So when there is a 5 in front of oxygen, there's a 6 in front of water. 5 in front of oxygen, 6 in front of water. I already laid out my units so they cancel. Top unit cancels bottom unit. And then now we just need the sort of missing entries here. First one here would be molar mass of water. So hopefully from the periodic table, you can go 18.02. If I crack open a box, well, that's just an Avogadro number. You can type that all in one long row, and that way we don't accumulate any accidental rounding problems. 25 divided by 18.02 times 5 over 6 multiplied by Avogadro's number, and I'm getting, do a mental check, I'm expecting it to be a huge number. I'm getting like how many molecules, when I'm talking about sort of molar amounts, I would expect to have a lot. A very common problem I get people say is, oh, I get 6.96. Well, first thing, you don't get 0.96 of a molecule, and they drop out this. Sometimes the calculator really push into the side here, and it's easy to forget to write down, but that actually puts you into the right power of 10, so that's super important. So let me just draw for you the summary map here. You know, that mind map that we started introducing here. I'm going to just sort of match it up for you. We'll look back at how we set up a 1-step, 2-step, 3-step in this lesson here. So far in my summary diagram, we did start seeing mole is in the middle of everything. This time we're actually comparing different chemicals, so I'm going to specify moles of A. If you look at all your conversions, we know moles to a certain number of particles here. Well, 1 mole was Avogadro number, defined for carbon, but then I just borrowed it for every other chemical. Depending on the chemical itself, we can go moles over to mass. This one here was our molar mass, and what we did is we ended up using our periodic table. Periodic table gives you element by element how heavy things are. We actually ended up having 2 bubbles for volume. The first bubble that we saw was for a gas at STP. We had molar volume. We did that derivation in the warm-up today here. For molar volume, 1 mole is equal to 22.7 liters, or decimeter cube. The one that I haven't practiced yet, I'm going to do it in the next question with you here. The last bubble for volume, this one here instead was a volume of solution, when I actually dissolved solids into liquids, and this one it really depended on that exact orange juice that I made. This time it depended on concentration, and concentration was moles per volume. So far my summary map here have been moles in the middle of these conversions. You could interconvert between them. Now what I've done is I've given the recipe, and I've said, okay, the recipe actually gives you the ability to compare moles of one chemical to moles of another chemical. So let's imagine having moles of B. It could be reactant to product, it could be reactant to reactant, product to reactant. The new conversion, believe it or not, all I've taught you in today's lesson is actually this guy here is called the mole ratio. To jump from one chemical to the other chemical, you use the balance equation. You use those coefficients to actually jump from one to the other. But now that we have moles, we're back to being able to, oh sweet, we can go back to number, use Avogadro number. We might be a totally different chemical, so our molar mass would then be different. We might have volume of gas again later on. Gas STP, we can use the 22.7 again. Or maybe I have a totally different solution. We'll see in a titration problem. This is very common later on. Volume of solution. And therefore, we are able to jump from one chemical to the other chemical and piece together what we've been learning before. So if you compare back to the questions we've done so far, the very first question was looking at moles to moles. So a 1-step conversion was just this conversion, was just practicing the new conversion. When I did my 2-step conversions, what I started asking you, let me see if I can reread it here. It's asking you for mass of one chemical, giving you moles of the one chemical. So if I start off with moles, I'm interested in mass, you're going to see the first conversion is just mole ratio, and then I want to go up to mass. Or my other conversion here was how many liters of NO gas if I have moles. Again, I'm starting off with moles of this one. I can go mole ratio first, and I can do liters afterwards. My 3-step conversion here, let's see if we can place ourselves. My 3-step conversion started from 25 grams. This time I'm not starting with moles. I'm actually starting with mass. I'm actually interested in molecules. I'm interested in getting numbers of a totally different chemical. You're going to see our conversion. First do molar mass to get to moles of your first chemical. Then do the new mole ratio step to jump from water over to oxygen, and then use Avogadro's number. You see the summary diagram here will actually help predict for you how many conversions it's going to take. They won't all be 3-step conversions, even though I would say 3 steps are the hardest style, but definitely using this map here. I'm not going to provide it on any quiz or test, but nothing's stopping you from drawing it for yourself. What you're going to find is as you do more practice, you'll be really good at this. Just for completeness sake here, before we do one final question, I mentioned to you the mole ratio works. The coefficient recipe works whenever we're comparing counting numbers. Technically speaking, the mole ratio would actually work between these two as well. So let's just call that a molecule ratio. So if I have 4 molecules of ammonia, I don't necessarily need to, let's divide out Avogadro, then go mole ratio, then multiply Avogadro again. The mole ratio will always work whenever we're comparing counting numbers. We also did Avogadro's hypothesis. Maybe I'll practice one with you in tomorrow's lesson. For Avogadro's hypothesis, we saw that as long as we have the same temperature and pressure, doesn't necessarily have to be STP, but STP is convenient for us. We knew that it didn't matter the identity of the gas. we're going to find that the mole ratio also works between volume and volume, but in that case they're only gas at the same temperature and pressure. I do want to emphasize there, this is not necessarily going to be STP. I could be at some totally random temperature, totally random pressure, but as long as we keep at that temperature, keep at that pressure, we're going to see that was called Avogadro's hypothesis. That gives us one new link. Aside from those two sort of obscure links here, we really have to go through moles, then I can really straight do mole ratio, and then convert over to whatever unit I want. So I'm going to finish off with this question here. Leave this for you to try. I'm going to take the compound lead-2 nitrate. It's going to react with potassium iodide. And in this case, you could predict this reaction. What I want you to do here is I want you to predict, balance, and classify. So that's why we did all that sort of predicting practice in an earlier section. And then just to introduce the stoichiometry of it here, I'm going to tell you Ki is actually aqueous, so Ki is actually a solution. So I'm going to give you some random numbers here. When 15 milliliters of 1.20 molar Ki, so that's going to be a solution. When that reacts, I want you to find what mass of precipitate forms. So what you're going to need to do here is actually quite a lot of practice. Actually, you'll need to predict, balance, classify. You should be able to pretty easy tell me a star replacement. Check through the compounds. This word precipitate, remember, it means this is a solid that crashes out of solution. If you check your solubility chart, you figure out which ones are aqueous, which ones are solid, you should find there's only one solid, and I'm interested in figuring out if I dried off the solution, evaporate off all the water, how many grams in a perfect world of this solid would I get? So you can try a question like that. I'm going to do something similar with you on the next lesson, but just do that for practice for now. Thanks, guys.